Hello students, this is the audio version of our t-test lecture from class. There are actually three different kinds of t-tests, but we're only going to review two of them in this audio lecture. You should also read the supplementary reading that is made available to you on Canvas for more details on both of these kinds of t-tests and the third kind of t-test that we will not be covering here in the audio lecture. The two kinds of t-tests we'll cover here are the independent samples t-test and the dependent samples t-test. For each t-test, the independent variable is a group variable, and the dependent variable is some kind of continuous variable that's measured the same way in each of the two groups. Independent samples and dependent samples t-test should only be used to compare two different groups. I'll explain the difference between independent and dependent groups in a minute, on one continuous outcome variable, or DV, that is measured the same way in each of the two groups. The independent samples t-test is used to compare the means of two different mutually exclusive groups of people or data. The dependent samples t-test is used to compare the means of one group of people at two different times. However, this group has to be measured the same way each time they are measured. So in the dependent samples test, the ability of an individual to be a member of the second group depends upon whether or not they were included in the first group. The exact same people need to be used twice, before and after an intervention. For this reason, you'll oftentimes hear dependent samples t-test using words like pre-test and post-test to refer to the measure of the dependent variable. Pre-test refers to measurement in the group before intervention, and post-test for after intervention. Let's start with a review of the dependent samples t-test in a little bit more detail. As noted, the dependent samples t-test is used to compare the same group of people, or the same group of cases, examined twice on the same continuous dependent variable. So for instance, we might look at whether or not depression scores differ before and after starting therapy, but depression scores have to be measured the same way, and they must be measured continuously. That would be using an interval or ratio scale of measurement. The t-test should not be used when the dependent variable is nominal. However, group membership could be nominal, such as being male or female. So the independent variable is a grouping variable and thus can be nominal, but the outcome variable must be continuous. That means it needs to be on the interval or ratio scale of measurement. Here we have two quick examples of times a dependent samples t-test might be useful. To examine depression scores for a group of 10 patients before and after starting medication. Before medication would be called the pre-test, after medication would be called the post-test. Or compare the mean ratings of confidence in statistics students before and after a group tutoring session. Before tutoring would be called the pre-test, after tutoring would be called the post-test. In order to run a dependent samples t-test, you will need to do the following. First, verify that you're using the appropriate test. Ensure that you have one grouping variable that will serve as the IV, which only has two different groups. Those groups must include the same persons before and after some kind of intervention. The outcome variable must be one continuous outcome variable measured in the same way at pre-test and at post-test. Then, state the research hypothesis and the corresponding null hypothesis. Most often in dependent samples t-test, a one-tailed hypothesis will be used. That means that we oftentimes have a directional hypothesis. For example, it would be a bit silly to be unsure whether or not we thought our intervention was going to increase or decrease depression. If we're giving some kind of therapeutic intervention, the hypothesis should be that depression will be lower after intervention, not higher. So oftentimes you'll see the advocacy for a one-tailed test being used here because there's likely to be, or at least the advocacy is that we should have a directional hypothesis when conducting a dependent samples t-test. You'll also notice that dependent samples t-tests are used a lot for experimental research. Then, determine the degrees of freedom corresponding to the test being used. The degrees of freedom for a dependent samples t-test are calculated as the number of cases, that is individuals, minus the number of groups they are broken into. Because these are the same persons before and after, It's actually only one group being measured twice. So the degrees of freedom are calculated as sample size minus 1, that is n minus 1. Then use the dependent samples t-test formula to calculate the obtained t-value. Examine that obtained test value against the critical value for that test using your critical values table, and then determine whether or not you have significance. If the obtained t that has been calculated with the data exceeds the critical value for that test in the critical values table, you can deduce that you do have significance. If, however, the obtained t value is closer to 0 than the critical value in the critical values table, we must accept the null and thus do not have a significant result. Here in the bottom corner, you see the formula for the dependent samples t-test. We have one new symbol here, that is d. But notice that the other symbols are things that we are familiar with, such as the summation sign, which you'll see repeated 3 times in the formula, n, which refers to the sample size, and then we've got some squaring, dividing, square rooting in this formula. The symbol we use for t-tests is the lowercase italic t, and you see that at the start of the formula, t equals, and then the formula. So we're going to use t as the symbol for this, the way we used r as the symbol for the Pearson's product moment correlation formula in a previous unit. D is used here in a somewhat similar fashion to group means for independent samples t-test, which I'll discuss in a bit. D is the difference score, D for difference. It refers to X minus Y for the participants. That would be the post minus pre for the participants. So post-test scores minus pre-test scores. The formula calls for both the sum of those differences for the group and the sum of those individual differences, which were each squared. So we've got here is, let's look at the top of the formula, sum of D. That means find the difference for each individual case, each person's post-test minus pre-test, and then add them all up. So you'll have to add as many D's as you have cases or persons in your data set. Now notice here I'll describe it as post minus pre, but you could actually set all of your calculations up as pre minus post, and it's not going to have an effect on your overall t-value or its significance, with the exception that it'll give you a negative t rather than a positive t if you would have otherwise yielded a positive t. It's the absolute value of the result of the t-test that is most relevant. So it's not actually going to have any impact on your ability to understand your data or infer significance if you do post minus pre or pre minus post, so long as you're consistent throughout the use of the formula. Okay. So the formula calls for the sum of the D's for each person. It'll also ask that we plug that number into the formula and square it. You'll see that in the bottom of the formula as the sum of D within parentheses and the square sign outside. So what that means is whatever we have on the top of the formula as sum of D is going to be plugged in twice. Once on the top of the formula and once to the bottom right of the formula where it asks for the sum of D in parentheses. But in the sum of D that's in parentheses, it will then be squared. Notice on the top of the formula, no squaring. Okay? The other thing we need is the sum of D's which have been squared. That means we're going to take each D for each person, square it, and then add it up. So the part of the formula that says take the sample size and multiply it by the sum of D's which have been squared, for that component, we're going to find the D for each person, then square each of those D's, then add all of those D's, and finally multiply them by n to get that bottom left-hand side of the formula here. If we're looking at our null and research hypothesis, you should notice that they are statements about the mean. The t-tests are about comparing group differences, so our hypotheses will be statements about group differences. The null here is going to say that the post-test mean of the population is equivalent to the pre-test mean of the population. The corresponding then research hypothesis or alternative hypothesis is typically a statement of direction. That is either that we state that the mean of the population at post-test will be higher than the mean of the population at pre-test, or that the mean of the population at post-test will be lower than the mean of the population at pre-test. So to be more accurate, if we have a directional research hypothesis here, the null will be a statement of pre and post means being equal or in the opposite direction of the research hypothesis. Now, you can state an inequality for the research hypothesis, but we typically advocate that it be directional for reasons that were discussed earlier in this lecture. Now, notice here I've got all of these terms written in relation to the population. But when we state our research hypothesis and apply it to sample data, we would switch that mu symbol you see there that looks like a little kind of cursive U with a tail to the X bar symbol when we're working with actual data. But the null is always going to be about the population. That's what we're trying to make inferences about when we're using inferential tests such as the dependent samples t-test. Let's take a look here at some sample data so we can do some calculations. Here we have pre-test scores and post-test scores noted in the table. As I mentioned earlier, we typically refer to post minus pre when we're calculating for D, but you'll actually see here that if you swap these columns, that is move the post-test to the left of the pre-test, without changing their names of course, you want to keep the names with their data, will end up yielding the same t-value, but it'll be positive or negative depending on which column we put to the left and which column we put to the right. What we're seeing here when we look at these data is the rows represent cases. So that first row with a pretest score of 3 and a post-test score of 4 refers to one person whose pretest score was 3 and whose post-test score was 4. Under that is one person whose pretest score was 2 and whose post-test score was 6, and so on. So you want to keep the data together, just like when we're running Pearson's product moment correlations. You need to keep the cases match their X's with their Y's, their pre with their post here. Okay, so let's look at the example here. Let's pretend that a researcher hypothesized that yogic breathing classes would increase students' ratings of anxiety. Here, this researcher thinks that this yogic breathing class is actually done so ineffectively that it's going to be problematic for individuals. To test this, she collected data on anxiety from a sample of 6 students before and after they took a 2-day relaxation course, which taught yogic breathing. Below are the data that I've just reviewed with you. Practice writing the hypothesis and calculating the t-value. Okay. The null hypothesis here would be that it's going to be a statement that pre-test and post-test scores are equal, or that post-test scores will be lower than pre-test scores, because the research hypothesis stated here is that post-test scores will be higher than pre-test scores. Now, before we even move on to doing any calculation, let's just look at the data and see if they are seeming to support the research hypothesis that post-test will be higher than pre, or the null that these are equal, or that the pre-test will be higher than post-test. When I'm looking across these numbers, for person 1, their post-test score is higher. For person 2, their post-test score is higher. For person 3, their post-test score is higher. Person 4 is equal at pre and post. Persons 5 and 6 are higher at post. So in almost all of the cases, I'm seeing a higher post-test score than a pre-test score. So that's giving me some good indication that the research hypothesis might be supported. Now on this slide, I've shown the calculations for D and D squared. In my D column, what we have is the pre-test score minus the post-test score. As I noted before, you can actually flip these around and do post minus pre, which is what is typically done, in which case you'll see the exact same numbers but without the negative sign in front of them. So the D's we have here are -1 because that's 3 minus 4 equals -1, -4 because 2 minus 6 equals -4, and so on. The sum of D here is 12. Had we done post minus -12, had we done post minus pre, our sum of D's would have been positive 12. And here I have the means just for my own interest, but you can ignore those on this slide. This final column gives us the D's squared and then the sum of D's, which have been squared. So for person 1, their D value is 1, 1 squared is 1. For person 2, their D value is -4, that squared is 16, and so on. And when I add all of the D squared values, I get 38. You should always have a positive number for your sum of D squared, because even a negative becomes a positive when it's squared. So if you've got a negative number here for your D's squared or for your sum of D's squared, that's telling you you've made a mistake about the signs of the numbers. Now let's plug these pieces into the formula. Here I've shown the steps to the top left, and the formula is retained down here at the bottom right so you can see the parity. If we're looking at the formula over here for t in the corner, we see that what should go on the numerator is the sum of d. Well, our sum of d was negative 12, so we'll plug that in. Now let's look at the bottom. We're going to have to square root after doing some other calculations. We need to first get the sum of d's which have been squared, which was 38, and multiply that by the sample size, which is 6. So that's one component we need down here. After we get that, we're going to subtract the sum of d's, which have been squared. Our sum of d's were negative 12, so we want to subtract negative 12 squared, which is going to be 144. Don't forget that a negative squared becomes a positive when you're doing your calculations. Okay? So once we have those pieces, which will be equal to 228 minus 144, we need to divide by the sample size minus 1. So we need 228 minus 144 divided by 6 minus 1. That yields for us then a numerator of negative 12 and a denominator, once we square root, of approximately 4.10 after rounding. When I divide negative 12 by 4.10, I get a t value equal to negative 2.93. If you got the answer 2.93 positive, that's just because you did post minus pre, or I did pre minus post, but this will not affect whether we are able to discern significance. Once we have these values, we also need to find the mean and standard deviation so that we can complete an APA format write-up. Because the t-tests are comparisons of group means, essentially, we want to report the group mean so the audience can see exactly what's going on. That is, if I'm saying the mean anxiety is expected to be higher after yogic breathing classes, it would be very helpful for our audience to see the mean values at post-test and at pre-test so they can discern what we are seeing in the data. So we always want to provide mean and standard deviation anytime we're doing a t-test. So here I have an example of an APA write-up where we start by stating whether or not the hypothesis was supported and reiterating what that hypothesis was, provide the means and standard deviations for pre-test and post-test, and then follow it up with that familiar string of numbers that we've been using in APA format. So let's just look at that string of numbers at the end first before we read the full statement, where you see comma, t of 5 equals negative 2.93, comma, p less than 0.05. That t is referring to the test we used, a t-test. That 5 in parentheses is referring to the degrees of freedom, which for a dependent samples test is n minus 1. Then we have that equal to the obtained t-value, which if we look at the previous slide was negative 2.93. And then I ascertained the p-value by using my significance level by using the critical values table. I looked in the critical values table for a one-tailed t-test with alpha set at 0.05. That means we wanted to be 95% confident when we had 5 degrees of freedom. And I found that our obtained value of 2.93 exceeded the critical value in the t-test table for a one-tailed test with alpha set at 0.05 and 5 degrees of freedom. So now I've got everything I need to put together my full APA write-up. Notice here I have not shown you how to calculate the mean and standard deviation because at this point in the semester it is assumed that you know how to do this without having to be shown each time. If you're not sure how to find the mean and standard deviation, you need to review our previous lecture and notes so that you can refresh your memory on how to use those formulas. And I do encourage you to practice them by hand because they will show up on future assignments and exams. All right, so here's our write-up. Consistent with the hypothesis, students had lower mean scores of anxiety before taking the yogic breathing class. The mean was 3, the standard deviation was 1.79. Then after, the mean was 5, the standard deviation was 1.26. T of degrees of freedom 5 equals negative 2.93, comma, p less than 0.05. So here we've shown that anxiety was lower before compared to after, and we're showing that the t-test tells us that the difference from pre to post is large enough to be unlikely to be due to chance. That p less than 0.05 means we're at least 95% sure that this difference in the mean scores is not due to random chance. Now let's move on to a review of the independent samples t-test. The independent samples t-test is used to compare two different mutually exclusive, that means non-overlapping groups on the same dependent variable. So the IV is a grouping variable where the groups must be different people. The same person cannot be in both groups. And the outcome variable should be the same kind of variable we would use for a dependent samples t-test. That means the outcome variable must be continuous, something that would be on an interval or ratio scale of measurement. And the outcome variable, the DV, must be measured in the same way for both of the groups. Let's take a look at two examples of questions for which this test would be appropriate. Do men and women have different mean levels of depression? Here we're assuming a gender binary, so assuming that everyone in our sample either identifies as male or female or as a man or a woman, we would have two different groups of persons with no overlap. Each of these groups would have to be measured the same way quantitatively on a scale of depression. Let's look at another example. Do students who have and have not had tutoring differ in their mean test scores? So here, persons cannot be in both groups. A student either has attended tutoring or they have not, and students in both groups are being measured in the same way. So we're using the same mean test scores or the same measure of test scores to get the mean test score in each group. Remember, this test is only appropriate when the two samples consist of different people. There can be no overlap or else you cannot use this in any meaningful way. Let's take a look here at the formula. Now, before you get overwhelmed by this formula, I'll point out the same thing that I typically point out in class, which is the top of the formula is telling you the main focus of the formula. So the independent samples t-test is really just a way of looking at whether the mean in group 1 is different from the mean in group 2, or rather how different the means in group 1 and group 2 are from each other. The bottom of the formula can be thought of simply as a way of adjusting the differences in means between group 1 and group 2. So the top of the formula is the main focus. The bottom of the formula is an important adjustment being done to that main focus. So let's take a look now at the bottom. Since we've already noted that the numerator, the top of the formula, tells us the main focus is to find the difference between means. But we're going to have to adjust that based on the sample sizes and standard deviations of the two groups. Notice that though there's a lot of stuff, a lot of pieces going on in the denominator of the formula, none of these pieces are new. So we've got n minus 1, well, we've seen that before because we use n minus 1 in previous formulas, including in the standard deviation formula for samples. We've got s squared, which refers to variance or standard deviation squared. Don't forget that standard deviation is the square root of variance, and variance is the squared of standard deviation. So if you know standard deviation, you can get variance by squaring it. And if you know variance, you can get standard deviation by square rooting it. Don't forget that relationship because it's going to become important here. Okay? The only other thing we have here then is total sample size, which would be n of 1 and n of 2 minus 2. So there's no new pieces here. We're used to using n's, we're used to using variances. But we have to note here that we have two different n's. N sub 1 means the sample size for group 1. N sub 2 means the sample size for group 2. Similarly, s squared sub 1 means variance for group 1, and s squared sub 2 means the variance for group 2. Remember, the subscripts are just naming variables, so 1's towards the bottom of any symbol means group 1, and 2's towards the bottom of any symbol means group 2. So the adjustment being done at the bottom of the formula only involves sample sizes for group 1 and their variances, and sample sizes for group 2 and their variance. Now notice here we have a piece that says n sub 1 plus n sub 2 minus 2. This is the degrees of freedom calculation for an independent samples t-test. The degrees of freedom for an independent samples t-test are calculated as the total sample size minus 2. This is the same thing as saying group 1 minus 1 plus group 2 minus 2. That is, the degrees of freedom in an independent samples t-test is equal to the number of pieces of data you have, that's each person, minus how many unique groups that you've put the people into. We will have two groups here because an independent samples t-test is always used to compare just two groups. So the degrees of freedom will always be group 1 minus 1 plus group 2 minus 2, which is the same as saying group 1 plus group 2 minus 2. All the people minus the number of groups they've been split into. So the bottom here is adjusting for sample size and variance. The reason sample size and variance are important adjustments is because those are two things that are implicated in how much error we might have in our means. The independent samples t-test is a comparison of the mean of one group to the mean of another group. But if the group sizes are unequal, we will have unequal assurance in how accurate our means are. Because remember, the more people we have in a group, the less error we think we have in our estimates for that group. That means the more people we have in one group, the more accurate we think the mean is for the sample to the mean of the population, because a sample mean is used to estimate a population mean in inferential statistics. But if my two groups were grossly unequal, such as if I had 10 people in group 1 and 100 people in group 2, that would mean that my estimates for group 2 probably have less error because there are more people than my estimates for group 1. So the bottom of the formula deals with that by taking into account the sample sizes and essentially aspects of whether or not they're equal. The other component that is implicated in our potential error in our means is the variance. Remember that the variance and standard deviations are estimates of variability of individuals from their group's mean score. So the greater the variance, the less accurate the mean is for each individual in the sample on average. The smaller the variance, and thus the smaller the standard deviation, the more accurate the mean is as an estimate of each individual in the sample. So if our two groups have equally low variances and thus equally low standard deviations, that means the means are equally good estimates of individuals in each sample. But let's suppose that one of our groups has a variance of 10 and the other group has a variance of 2. What this would indicate is that those persons in the group with a larger variance have mean estimates that are less accurate for each individual. That means are more distinct from person to person. That is, the mean is not as good at capturing any random individual in the sample as they would be in the group with these smaller variances. So because larger sample size means less error in estimate of the mean, and smaller variance means less estimate in our estimation with the mean relative to the population. Both of those things are accounted for in the bottom of the formula as ways of adjusting the mean differences. Okay? So the shorthand of this, again, is the top of the formula tells you that the main focus is to look at differences in the group means, and the bottom of the formula deals with things that could impact the accuracy of those estimates relative to each other. That is, each group's sample size and each group's variance has an impact for the potential error in the estimate, that is, error in the mean as an estimate of the population. When we wish to run our independent samples t-test, we need to do several things in order. First, verify that we are using the appropriate test. If you have 3 or more groups, you should not use the independent samples t-test. If you have only one group, you should not use the independent samples t-test. If you have 2 groups and they were not measured in the same way on the outcome variable, you should not use the independent samples t-test. It should only be used to compare the means of 2 different non-overlapping groups on the same outcome variable that has been measured in the same way. Then, state the research and the corresponding null hypotheses. Determine the degrees of freedom corresponding to the test being used. The degrees of freedom, as noted for an independent samples t-test, is group 1 sample size plus group 2's sample size minus 2. So that's total sample size minus 2. Then calculate the t-value using the formula from the previous slide and examine that obtained t-value against the critical value for the test that you find in the critical values table. Use that to determine significance. If the obtained t-value is greater in absolute value than the critical value in the critical values table for that test, the result is significant. If the obtained t-value is lower in absolute value than the critical value from the table, that means it's closer to 0 than the critical value, then we retain the null and we do not have significance. So as noted, you want to verify that you're using the appropriate test before starting. I've already described that in detail. When we run our test, we're going to want to find the components necessary, that is the mean for each group, the variance for each group, and the sample size for each group. So that means we're going to have 6 important pieces here. when we're using our test. We want to state the research and the null hypothesis. So, for instance, we could use the general null for independent samples tests, which states that the mean of the population for group 1 will be equal to the mean of the population for group 2. If we have a directional hypothesis, we'll state which group will have the greater mean. Here I've noted X bar because this is typically about a sample when we're testing the hypothesis. So we might state that group 1 will have the higher mean than group 2, or that group 1 will have the lower mean than group 2, using the symbols that you should be familiar with from previous lectures, because we used similar symbols when we were talking about correlation. If we have a non-directional research hypothesis, we'll simply state that x bar of 1 is not equal to x bar of 2. If we have a directional hypothesis, that will warrant a one-tailed test. If we have a non-directional research hypothesis, that will warrant a two-tailed test. Here you see an abbreviation and description of the degrees of freedom. You'll see two ways to calculate, which will yield for you the same degrees of freedom. It'll be total sample size minus 2. Then we need to plug our data into the equation and solve. Again, the 6 pieces we will need are the sample sizes for each group, the mean for each group, and the variance for each group. You could also find the standard deviations for each group and plug it in squared, which is the same thing as plugging in the variance. After we have obtained our t-value, we'll examine it against the critical value and use that to determine our significance. If we have time during our semester, we will practice this in SPSS, and I'll show you later in this lecture what some SPSS output might look like and show you how to find the important components to assess significance using SPSS software. As noted, the test is impacted by variances. Thus, if the variances are highly unequal, we may have to do an adjustment for the independent samples t-test. When we are calculating by hand, this will not be an issue. However, if we are calculating with real data, it will be an issue. The reason it will not be an issue calculating by hand is because I'll always give you fake data that are much cleaner than may occur in real life. That means when I give you fake data to practice with in class, the variances will not be significantly uneven. That means the variances of the two groups will be similar enough for us to move forward and use the formula without any issue. However, I want to point out that if you're using the independent samples t-test and the variances between the two groups are very different, that is, they're significantly different, and we have a test for that, then it may impact the formula and an adjustment needs to be made before we can assess significance. We will not be doing that adjustment ever by hand in our class, but we will examine it visually using SPSS output. The test that we use to assess if the variances are unequal between the two groups is called a Levene's test. The Levene's test for variances or equality of variances is used to compare if the variances in the two groups are so different that we are 95% sure they are representing a real difference in variances, or at least one that represents a real difference in the population. This is the same criteria we've been using for all of our tests so far, for the correlation, for regression, and now for t-test. So we will not calculate Levene's by hand, but I will note it for you later when we're looking at output with SPSS. Here, I'll just point out that when we're looking at the variances or standard deviations for our two groups in an independent samples test, they'll want to look at whether the variances look visually similar or not. Okay, so let's try that with some data here. I've given you scores for two groups of data and a hypothesis. Okay? The scores in this table are for test anxiety for two groups of students. Group 1 has taken a test prep course which stressed relaxation. Group 2 did not take this relaxation course. Anxiety scores are on a 9-point scale. Let's look at our raw data here. Okay? It looks like the scores are low in group 1 compared to group 2. If I look at group 1, I've got 1 and 3 2s. Those are pretty low scores. If I look over at group 2, I don't have any 1s, and I only have one score of 2. So I've got 4 low scores in group 1 and only 1 low score in group 2. Now I'm going to look at this in reverse. Let me look at high scores. High scores would be things like maybe 6, 7, 8s, and 9s. But I don't even see any 7, 8s, and 9s. So a high score relative to the scores possible here are 5s and 6s. So I'm going to look in group 1. I only have one high score of 5. In group 2, I've got two high scores, a 5 and a 6. I've also got two scores of 4, and there are only one score that's even 4 or higher in group 1. So what I'm seeing is many low scores in group 1 with very few high scores. And in group 2, I'm seeing very few low scores with many moderate and high scores relative to what we're seeing across all of the scores in the tables. So I might hypothesize then that those who have taken the test prep, that's group 1, have a lower anxiety than those who did not, that's group 2. If I do this, that will be a directional hypothesis and that will require a one-tailed test. But maybe I didn't look at these data and I just said, well, I'm not sure what's going on, I'm not sure what to expect. So I just think the two groups will have different means, but I'm not sure who will have the higher or lower mean. That would be a non-directional hypothesis and thus would warrant a two-tailed test. Let's review again our formula down here in the corner before we start gathering our pieces. The formula requires the mean for each group, the sample size for each group, and the variance for each group, or the standard deviation squared. We'll need to find then 6 things: the mean, standard deviation, and sample size for each of the two groups. Our hypothesis here might be that the two group means will be equal. If I state, however, that I should have a one-tailed test, that is, I state that group 1 will have lower anxiety scores than group 2, then the null wins if the group means are equal, or if I see that group 1 has the higher mean score. Okay? So here we'll stick with the one-tailed example towards the bottom and assume that our null hypothesis then is for equivalence or for group 1 having higher anxiety. Our hypothesis will only be correct if group 2 has significantly higher anxiety than group 1, as shown here in the example for the one-tailed test. Here I have calculated the 6 pieces. I'm not going to walk you through in the slide how to find the mean and the variance or standard deviation, because you should know how to do that already. Okay? My mean for group 1 was 2.5 and my sample size for group 1 was 6. My standard deviation for group 1 was 1.38 and my variance was approximately 1.90. That's 1.38 squared. I'm going to be plugging in the standard deviation and then squaring it. If you prefer to use the shortcut, you can just plug in the variance, which is 1.90 approximately. For group 2, I had a mean of 4, a sample size of 6, and a standard deviation of 1.41. The standard deviation squared, that is the variance for group 2 that I yielded, was 2.00. You might get something like 1.99, which is fine. That's just rounding differences where we were rounding our steps. I'll be plugging in these S values and then squaring them, but you can plug in them the variances, that is the S's that have already been squared. Here I've broken my formula down into two parts, the numerator first and then the denominator. For my numerator, I simply take x bar 1 minus x bar 2. That's the mean of group 1 minus the mean of group 2, which yielded for me a difference of negative 1.50. That negative means that group 1 had the lower score. If group 1 had had the higher score, the numerator on top would be positive. So I already know that I'm going to have a negative t value because my numerator is negative. Then let's look at the components of our denominator. I'm going to start with the left side under the square root sign in the denominator. I need the sample size minus 1 for group 1, which is 6 minus 1, or 5. And I want to multiply it by the variance, which is 1.38 squared. I'm then going to add that to the degrees of freedom in the second group, that is the sample size minus 1, or 6 minus 1, which is equal to 5, times the 1.41 squared. Okay? Then I'm going to divide this whole thing. So I'm going to find the sample size minus 1 times the variance for each group, add those together, then divide that by the degrees of freedom, which is the two sample sizes added together minus 2. So for this whole side, the first brackets, the brackets to the left in the bottom of the equation, I get a total of 1.95. Now let's look at the second side here, the brackets to the right side where it says n1 plus n2 divided by n1 times n2. So here I'm just going to plug in the sample sizes. That's going to be 6 plus 6, which is equal to 12, divided by 6 times 6, which is equal to 36. So for the brackets to the right, I get 12 divided by 36, which is the same as 1/3, or 0.333. I'm going to round that here to 0.33 for ease. Let me put all my pieces back together. For the numerator, I have negative 1.5. And under the square root sign in bracket 1, I have 1.50 on the top. In the bottom here, in the brackets to the left, I have 1.95. In the brackets to the right, I have 0.33. So I'm going to multiply 1.95 times 0.33 and then square root that value. So I get 0.64 square rooted, which is equal to approximately 0.80. I'm going to take the numerator of negative 1.50 and divide it by that denominator of 0.80, and this yielded for me an overall t-value of approximately negative 1.87. If you got negative 1.86 or negative 1.88, that's fine. That's just rounding error in where you were rounding versus where I was rounding in my steps, because I started rounding to 2 decimal places early on in the formula. Okay? So what you'll see here is that the t-value is similar to the numerator, but there has been some adjustment made. So it's not the same as just x minus x or x1 minus x bar 1 minus x bar 2. It's those after some adjustment. So we see our t-value is a little bit different than the numerator value. Here I've copy-pasted for you an example of the t critical values table that you have available to you on Canvas and that we've been using previously during this semester. Notice here that you want to find your degrees of freedom, set your alpha at 0.05, unless otherwise stated, and then choose whether you have a one-tailed or a two-tailed hypothesis so you can find your corresponding critical value. Remember, the critical value is the one you must exceed with your obtained value to be 95% sure that you can reject the null hypothesis without a type 1 error. That means this is the number you have to exceed in absolute value to have a significant result. Choose the critical value that matches your hypothesis and take note of the fact that the critical values, that is the thresholds you have to surpass, differ dependent upon whether you have a one-tailed or a two-tailed test for reasons we've previously reviewed. For this test, we have 10 degrees of freedom. If we set our alpha at 0.05 and we have a two-tailed test, our critical value is 2.228. If it's a one-tailed test, it's 1.812. Here I've noted for you the pieces we could use in our equation, and I already plugged those in on the previous slide, and we yielded that result of approximately a negative 1.87 or a negative 1.86, depending on where you rounded. The results in APA for a two-tailed test would be written using these components at the end, that is, T of degrees of freedom equals obtained value, comma, then we're going to put whether the result was significant or not. If I compare my critical value in the critical value table to what I've obtained here, I actually find that my value does not exceed the critical value in its absolute value, so when I ignore the negative sign. If I use my critical value table, I am looking for a one-tailed test where we have 10 degrees of freedom, and we want our significance or alpha set at 95% or alpha less than 0.05. So when I find that critical value, it's actually over a 2, and my value is under a 2 in absolute value. I have a negative 1.86 or 1.87 depending upon rounding. So I did not exceed that threshold. That is, the null cannot be rejected, and thus I have to reject my research hypothesis and state that my finding does not show significant results in support of the hypothesis. So here I've put the two options for how we can write this. If I've used the critical value table to note non-significance, I'm going to put that italic P greater than 0.05 comma NS, the NS standing for non-significant. However, if I used SPSS, it'll tell me the exact chance of a type 1 error. That is the exact chance that the null is actually correct here. And that will tell me that it's about 0.09 or a 9% chance that we are wrong and the null is right. That's a 9% chance of a type 1 error. That's over the 5% we're willing to accept. So if I had done this using a computer program to get the exact chance of a type 1 error, I could actually write P equals that number, comma, NS to denote non-significant results. Okay? But I'm going to stick with just doing it using our critical values table, and so I'm going to state that P was greater than 0.05, non-significant, when I did a two-tailed test. However, if we had run this as a one-tailed test, you can look over your critical values table, you will find that we actually do meet the criteria for significance. So the critical value for a one-tailed test was not the same as the critical value for a two-tailed test, even though our sample size and our alpha level were set the same. The reason for this is, as you'll recall, that we need to be further from zero. That means we need to have a more dramatic result in a two-tailed test in either direction than we need to have in a one-tailed test in the appropriate direction, that is the one consistent with the hypothesis, to find significance. If you're still unclear on this concept of why you need a larger value for significance in a two-tailed test compared to a one-tailed test, you should review your notes and speak with me in person so we can review it one more time, looking at the normal distribution curve and where we're setting our boundaries for significance. So what we've got here is a really interesting case where we're close to the boundary for significance, where in a one-tailed test we would meet the criteria for significance, we did exceed the critical value, but in a two-tailed test we do not. And thus it becomes really important, or it's clear here, why it is so important when we set our hypothesis to choose a one-tailed test if we have good reason to believe we know which direction the result is going to go. If we are really uncertain, then a two-tailed test should be used because we don't want to lose the possibility that we're going to look in the wrong direction. But if we have previous research or good theory to tell us which direction to look, which direction to posit our hypothesis, such as that group 1 will have the lower score, then we should move to using a one-tailed test to increase the likelihood we're going to have a significant result, if indeed our hypothesis is correct. As noted, you can run these analyses using SPSS. I will not walk you through all of that in detail here, but instead I've given you a summary slide of how you would run these data in SPSS. You would first need to open an SPSS program and create two different variables. You would want to set up your data, so you have one variable which is called your grouping variable, and your second variable which is your DV, your outcome variable. So if I were going to enter these data, I would have a grouping variable, which I would just call group, and I would call group 1, 1, and I would call group 2, 2, and then for everyone in group 1, I would code them as having a score of 1 in the column for group in SPSS, and all the persons in group 2, I would code them as having a 2. Remember, 1 and 2 here for a grouping variable for nominal data do not indicate more or less of something. They refer to differences in kind or differences in quality. So being a member of group 1 means you're not a member of group 2. It doesn't mean you're less of something than members in group 2. The other variable you would need to have here is not nominal, but instead should be on scale. That means we assume that it's interval or ratio. So my second variable here would be the scores for anxiety for these individuals. So each person would have a score for group membership, that's a label of 1 or 2, and then right next to it a score in their anxiety column on that scale of 1 to 9, and those scores were 2s, 3s, 4s, 5s, and 6s for most persons. Once the data are set up, you'll click on Analyze. That's on the top of any sheet when you're in SPSS. So you can be in Data View, Variable View, or even in the Output window. And you'll click on Analyze, then scroll down the drop-down menu to Compare Means, and then select Independent Samples t-test. Then set up and run the test. When we run our results in SPSS, we'll want to write them up using all of the information. Here I have some additional information that goes beyond the scope of our textbook, but can be useful to you if you plan to actually use real data in a system such as SPSS in the future. So here I'm going to show you not only all of the write-up we would have done by hand, but I'm also going to show you how to write up that Levene's test. Remember, there's the assumption in this formula that the variances between the two groups are not significantly unequal. That means the assumption is that group variances are similar before we run an independent samples t-test. If they are not, an adjustment is needed. So I'm going to show you how to write here for your more sophisticated sets audience, if you're actually working with real data in the future, how you would show your audience that you did not violate the Levene's assumption of equality of variances. So here's an example write-up for the data that we've already worked with. An independent samples t-test was run to assess whether those who did and did not take a prep course differed in their test anxiety. Levene's test showed that group variances were not significantly unequal. F equals 0, P equals 1.00, non-significant. That's what we want to see for Levene's test. Then we'll add here the results of the actual test of the hypothesis. Contrary to the hypothesis, those who took the prep course did not have a significantly lower mean score of anxiety, mean equals 2.5, SD equals 1.37. Then those who did not take the prep course, mean equals 4, SD equals 1.41. TF10 equals negative 1.86. P equals 0.09, or I could have written P greater than 0.05, comma, NS, non-significant. Here, the reason I'm putting it as non-significant is because I was assuming, or I was pretending when I was doing this practice run, that we had a two-tailed test, that we weren't sure if the class was going to work or what direction it was going to have an effect. So I ran it as a two-tailed test. If you go back through SPSS and run those same results, assuming a one-tailed test, you will get significance. Here's a quick cheat for you. If you've run things in a two-tailed test and you want to know what the results, what the p-value would have been in a one-tailed test. The p, that is the chance of a type 1 error, for a two-tailed test is always double the p of a one-tailed test. So here with my two-tailed test, my p, my chance of a type 1 error, is 0.09. If I divide that by 2, I get the p-value when it's a one-tailed test. That would be a 0.045. 0.045 is just under the 5% chance of significance. Because in a two-tailed test, I have twice as much possibility of a type 1 error overall relative to my obtained value because I'm looking in two tails, I'm looking in two directions. In the one-tailed test, we're putting all of our chance of being wrong on one side, so it's actually half of the overall chance of a type 1 error that is occurring. So I don't even have to rerun this in SPSS to know if this would have been significant as a one-tailed test, because I can take this p equals 0.09 and divide it by 2 to know what it would have been for a one-tailed test. Conversely, if I had run everything as a one-tailed test and I wanted to know if it would be significant as a two-tailed test, I would just multiply the p-value, that is the chance for type 1 error, by 2 from a one-tailed to find out the significance level for a two-tailed test. So that's just a little side note here. Let's take a look at how you might set these up for a dependent samples t-test in SPSS. So here I've set up some fake data for a dependent samples t-test, and here I'm showing you the window where you would fill in what you want for the dependent samples t-test to be run in SPSS in case you're doing this outside of class time. So in SPSS, it's going to call a dependent samples t-test a paired samples test. These are synonymous. You can use them interchangeably. In our class, you can refer to a dependent samples test as a paired samples test whenever you would like. They mean the same thing, paired and dependent samples. But SPSS will always use the term paired, so that's the one you'll need to keep in mind when you're calculating or running analyses rather using SPSS. To set up our data, we do it a little bit differently for a dependent samples test. Instead of having one column where I put the group, like 1 or 2, and the other column where I put the outcome, instead, we put the outcomes in two different columns, the outcome at pre-test and the outcome at post-test, because we have a mean of pre-test and a mean of post-test. And then I'm going to fill in the person's scores on the same test at pre and post. So here we see at 3 and next to it is 7. Those are the scores for the same person before intervention is 3, after intervention is 7. Below that are the scores for person 2, below that for person 3, and so on. So it's a little bit different than how we would set it up if we were doing an independent samples test. Then if I want to run it, I'm going to click on Analyze. Then in the drop-down menu, I'm going to choose Compare Means, and then Paired Samples t-test rather than dependent because the term dependent doesn't appear in SPSS. Then I've got here, my two variables will show up as my optional variables for use in the left hand. And I'm going to scooch them over one by one to where it says Paired Variables on the right. Remember, the data that you have to work with will appear on the left in SPSS when you're using a test run box, when you're setting up how you want to run things. And then the things you're telling it to use will be moved over to the right. What we typically do here is move post first and then pre second. So I would click on post and then the arrow to move that over under variable 1. Then I click on pre and then the arrow to move that under variable 2. And then on the right you'll see pair 1, post test, and next to it pre-test. And then you'll be able to click the OK button. It's not highlighted here in the example because the data haven't been moved over, so there's nothing to tell it to do. Here I have the output for those fake data I've shown you on the previous slide. This is how SPSS will spit them out. It'll give me 3 different tables if I just ask it for kind of standard information. Okay? Here it's for variable 1, that's going to be our pre-test, and for variable 2, That's going to be our post test here. So we did pre first and then post second, which is similar to how I've been doing them when I was setting these things up by hand earlier. Okay, so you can do post minus pre, which is usually preferred, or pre minus post, which you'll see that I tend to do because I ignore the sign and just look at the overall t-value. Okay, so what it gives me first is the means and the standard deviations for each group, as well as the sample sizes. So I've got mean, sample size, and standard deviation for group 1, mean, sample size, and standard deviation for group 2. Down here at the bottom, we see the overall mean difference between the two groups. That's going to be the mean of one minus, or the mean of one of the groups minus the mean of the other group. So it's telling me that it's a negative 2.60 because it took 4.6 and subtracted 7.2 to get the overall mean difference. Then what we really want to look at is the obtained t-value. If you look at that bottom table, the third column from the end is labeled t. See that little t? And under it, it says negative 7.005. That means the obtained t-value for these data is negative 7.01 if we round. The degrees of freedom are 9 because our overall sample size, the total sample size, is only 10, and degrees of freedom is overall sample size minus 1. Notice here that the sample size is not 20 because if we look up at the top where it's saying the sample sizes for each group, those same people have answered those questions twice. So it's not 10 people plus a new 10 people. It's 10 people answering before and those same 10 people answering afterwards. So our total sample size is only 10, and degrees of freedom here for a dependent samples test is total sample size minus 1. That last column in the bottom table tells us the chance of a type 1 error. That's our significance level, or the alpha. This is telling us that the chance of a type 1 error is 0.000. So that means that we can be 99.99% sure, essentially, or at least 99.9% sure of our result. So that's great. We are seeing there's far less than a 5% chance of a type 1 error, and thus we have significance here. So if I were going to write this up in a simple statement, I might say mean scores on post-test were significantly higher than pre-test scores, and I'm going to provide all the information. Anytime we do a t-test, independent or dependent, you need to provide the mean and standard deviation for each group, that is for pre and post in the dependent, or for group 1 and group 2 in an independent. Then we have to give all of our data the way we typically have at the end. Show the test symbol, which is t, next to it in parentheses the degrees of freedom, and show what the obtained value was. Here it was negative 7.01. Then give the p-value. Here I put p less than 0.001 to indicate that we have far less than a 1% chance of an error here, but we could have even just written p less than 0.05, which is what we've typically been doing in our semester. If I were going to run an independent samples t-test in SPSS, I would have set up the data as I described earlier. We'd have a grouping variable and give symbols for group 1 and 2, such as 1 for group 1 and 2 for group 2. And then next to it, we would have set up the dependent dependent variables data. So here, let's pretend that we had an independent samples test where we're comparing two groups on a memory test to see if group 1 differed from group 2 in their scores on a memory test. So here in the left, you see our two variables for use, and then to the right, we have to fill in what we want. The test variable in the SPSS window refers to the dependent samples test. The group variable, see that little tiny window towards the bottom, little tiny input area, that's for the group. So whatever our group is, that's going to go to the bottom. I'll click group and the arrow to move it into grouping variable. And then the dependent variable is called the test variable. So we're comparing the groups on their scores on a memory test. So I'd click memory test, then the arrow to move it into the test variables box, the big one on top. Now we've got one extra step here. When I put the group variable into the bottom where it says grouping variable, a little button will turn on that says define groups. It's under the grouping variable box. I'd want to click on that so I can tell SPSS what I used to name the two groups. So if I click on that, I get the little box that you see to the right here that says define groups. What it's asking you is to tell it what you called group 1 and what you called group 2. I like to always call group 1, 1 and group 2, 2 to keep things as easy as possible. So for me, I would put the number 1 in the box next to group 1 and the number 2 in the box next to group 2. Then I'd hit continue because then the box would highlight for continue. It would bring me back to my big box to the left, and then I would hit OK to run my analyses. If you have access to SPSS or you're in our lab during office hours when I have it open to you, you can practice using SPSS with the data shown here and on the following slide. So here's a second option of fake data that you can use to practice using SPSS, interpreting results, and engaging in a write-up. That concludes this audio lecture on t-tests.